the real world, not the flat protein world. And I want to give an example, and we'll do one. First one will be HB for hemoglobin Christchurch. Okay. This is an altered form of hemoglobin first found in a person in Christchurch, New Zealand. All right. It turns out there are hundreds, in fact, probably thousands of mutant hemoglobins known. Why is that? Because it turns out that you can mess up hemoglobin and be sick enough to need to see the doctor, but not so sick that you die, or sometimes they are, in fact, fatal or extremely debilitating. So it brings you to the doctor in a big way, but doesn't necessarily always kill you. So there's been lots of studies of odd versions of hemoglobin. And so there's tons of different ones, and they're typically named from where they were first found. So there's hemoglobin. I don't think there's a hemoglobin Boston, but there's a hemoglobin Ypsilanti, Michigan. There's a hemoglobin Christchurch, New Zealand. So wherever they were, some doctor, a patient showed up in the doctor's office with a blood disorder, and they turned out because they have an altered form of hemoglobin. And so this one was found in Christchurch. We'll talk about this one and one other one today. All right. And what I want to do is make kind of a big fat table here about what's going on with this particular altered beta globin and why it happens. So there's the type of beta globin. There's the beta globin amino acid number 71. So what do I mean by that? If you remember, there's 146 amino acids in beta globin, numbered 1 through 146. So 1, 2, 3, 4, 5, 6, 7, 8, whatever. Number 71, it turns out, is going to be important for this conversation. The side chain of number 71 and the phenotype. So there's two forms. There's normal, and it has phenylalanine. And phenylalanine side chain is CH2 and then this big fat ring thing. Okay. And again, you're never going to have to memorize these amino acids. You're going to need to be familiar with them for the exam, but you don't have to memorize the structure. So you tell me, philic or phobic? Phobic, big time. So your classic big, fat, greasy amino acid. So it's big and it's phobic in a big way. And the phenotype of this is normal. Right? In Christchurch, so not everybody in the town, but one person, it's been replaced by serine. And that does not mean that phenylalanine was transmogrified into serine. It means that the orders in that person, the gene for hemoglobin, was altered such that now when it makes beta globin, it makes it with the wrong amino acid in that one place. So that serine is CH2OH. Okay? And this is small. And is it philic or phobic? Philic, big time. I mean, it's not charged. It's fair. So I shouldn't say big time. It's definitely philic. All right? And the phenotype of this is what's called hemolytic anemia, which basically means your blood. So let me write that more neatly. Basically, your blood cells break. So anemia is like anemia, lack of blood, lack of function, reduced function in your blood. And hemolytic, hemo is blood, lytic is breaking, so your blood cells break. And so you have insufficient blood function. So anemia, you're weak, pale, you don't have a lot of energy because you can't oxygenate your tissues properly. Right? And there are many different flavors of anemia. Some of them are genetic, some of them are caused by toxins or whatever, diseases. This is one that it was inherited. So this person showed up with hemolytic anemia, and it turns out because of this amino acid change. And so the question you might well ask is, where is Phe7? So where is phi 71 in normal beta globin. So that will help us figure out what's going on here. So I'll come back to this in a sec, but let me switch over to some pictures. So this would be, I believe it's here, yes. So if you remember good old hemoglobin, right, big fat molecule, 4 subunits, 2 alphas, 2 betas. Here's hemoglobin Christchurch. So there's one of those beta globin subunits. And the yellow dots are all the rest of the atoms of beta globin. The gray thing in there, that's the side chain of amino acid 71. That's phenylalanine. First of all, where would you expect to find phenylalanine in a protein? On the surface or on the inside? The inside, because it's really hydrophobic. All right. Where is it in that picture there? How could you tell? Every time you see the gray, basically there are yellow dots over it. So what does that mean is, that's like saying I have to look through the rest of the protein to see that one, which means, except you can peek at it a little bit here, for the most part it's in the middle of the protein. It's buried in the hydrophobic core where you'd expect it to be. Okay? So that's unsurprising why phenylalanine should be in the middle with all of its hydrophobic buddies, avoiding water. Right? Questions about where that is before we talk about what happens when you change it? All right. So that's what it would look like. That's where the normal amino acid is. All right. So it's basically in the phobic core. And there are pictures of this, I forgot to say, in today's information-packed handout. Like on the second page of it, for example, you'll see there's a thing about Christchurch with a picture taken from that. It makes it easier to take notes on. So how does this happen? How does this lead to disease? So changes in the gene lead to changes in the primary structure. That is, phenylalanine 71 is, instead of making phenylalanine, you put serine at position 71. As a result, that leads to changes in secondary, tertiary, quaternary structure, leads to the disease symptoms. So again, it's not this person's disease is not because the disease somehow reaches in and changes that phenylalanine to serine, although we sometimes say things like that in shorthand. What it means is this guy inherited a gene with the wrong instructions. So instead of ordering a mushroom pizza, he's ordering a pepperoni pizza. Or that is, in this case, instead of ordering beta globin with phenylalanine at position 71, it's now ordering everything else is the same, except number 71 is changed, and now you're ordering serine at that position. And so here's the idea. So how does this work? Normal beta globin. If you drew a cartoon of it, you got water outside. Let me get a little more space. It's a nice little blob. Number 71 is out here, and you've got that CH2 and that big fat hydrophobic ring sitting in the hydrophobic core. There's water outside. And this thing is happy, energetically speaking, in the phobic core. All right, cool. In Christchurch, what you've got, the protein gets made, but at number 71, you have CH2OH. Different one. So the orders got changed. So you tell me, is serine going to be happy in the hydrophobic core of the protein? No. What would it much rather be doing? Sticking out. What can it do if it sticks out? It can bond with the water. What kind of bond? Hydrogen bonds. I mean, that OH is hydrogen bond city. It would love to make nice hydrogen bonds with water. So it's not going to want to be tucked in the middle. It's going to want to be pulled out. Right? And so when you make this protein, instead of saying tucked in the middle, it's going to be pulled out. And so so what happens is, number one, is that the philic serine would rather be in water, therefore it will be outside. So number 2, because all the amino acids in beta globin are connected through the backbone, you end up with a misfolded protein. That is something like this. I'll draw it cartoonishly like this, but basically CH2OH is going to make a hydrogen bond to water. All right, and this is number 71. So you might think it wouldn't, sorry, that CH2 is really even more horrible than usual. Let me just draw that over. Sorry, everybody. CH2-OH, and you got water, make an H bond. All right? So you might say, why doesn't just that one kind of pivot out? Well, it turns out when it does, it pulls a whole bunch of stuff with it, and basically sort of pulls the insides out of the beta globin, and the whole thing is folded wrong. Right? It's like if you wrapped up your wire thing, and instead of making one of those hydrophobic ones, you made a hydrophilic one, it would change the whole shape. And so that's what it does. As a result, because this protein is folded wrong, it turns out that clumps of misfolded protein, they are what's called Heinz bodies. These guys form, and as a result, in the Heinz bodies, weaken the red blood cells, and with the weaker red blood cells, the blood cells break. Blood cells break, and that leads to anemia. So it's a long story, but it gets to the end result. Proteins folded wrong. As a result, misfolded proteins tend to be sticky. Why do they tend to be sticky? Because their hydrophobic insides sometimes get sort of exposed. And so they glob together by the hydrophobic effect. And so if you remember, my analogy for the red blood cell was a beanbag chair, a great big bag full of beans. So it's loose and floppy. It can squeeze its way through your tiny little capillaries. If, on the other hand, instead of being full of little beans, it's full of, like, bricks of protein stuck together, that's going to be a whole lot less flexible, right? Or big logs or something. It's going to be a protein all stuck together. It's going to be less flexible. They're going to break open. So the misfolded protein is sticky, forms clumps, these Heinz bodies. The Heinz bodies, because they're big and lumpy, they make the red blood cells unstable. They break open, and you end up with anemia because you haven't got functional red blood cells. Questions about how that story works before we talk about what that means? Yeah. How do they figure this stuff out? They probably worked backwards. They probably saw this person was anemic, and they took a blood sample. They saw these things inside his blood cells, and then they, worked their way backwards to figure it out. Is most likely how it happened. Yeah. The Heinz bodies are bunches of misfolded hemoglobin all stuck together, or beta globin all stuck together, that gum up the works in the red blood cells. All right. What I want to do now